Okay, so we're going to continue with what we did last day. So I want to start sort of the generic form that we're going to be working with right now. Now the issue, and there will be issues, and most of these, like I said, are going to be the next lecture. The issues are going to be with this term right here. That's probably not going to be a constant right now. It's going to be a function, but we're going to limit it to polynomial functions only. Other functions can be there, but we can't use the power series in the same way we are right now if those aren't polynomial-ish things. What if this guy can be 0? That's the question. What if there are values of x that make it 0? So the first thing we do is we get rid of them, because I don't want that there. So then we rewrite the problem in this form. Not like this is new, right? Q of x. So obviously P is just A1 divided by A2. So now here's the thing. What if, okay, I need A2 of x at the very least, I need it to be analytic at 0. Because otherwise, when I divide through, I'm in trouble. And the way we're doing our power series, we're doing our power series centered about 0. We won't be able to do this problem in the same way if this guy can equal 0 at x equals 0. Now, if it equals 0 somewhere else, that's a non-issue. Okay? So what I need to know is where is P and where is Q analytic? So the author does a couple of really good examples. He does one where, for example, he uses a natural log as one of the coefficients just to illustrate. We're never going to do a natural log as a coefficient. We're not going to do sine or cosine or e to the x as coefficients because, again, when I change these to power series, I am making everything into a polynomial. So therefore, I can't have one of the numbers not be a polynomial or one of the functions. We wouldn't be able to continue. Okay, but again, it's as long as this is analytic at 0, I'm fine. Now remember, what does analytic mean?
You're able to differentiate it at 0.
How many times?
Infinitely.
Infinitely. So I think the easiest way to remember analytic is infinitely differentiable. Okay, remember, because we're looking at, if you remember how we constructed power series, today in my Calc 2 we did Taylor series. So I showed them, you have to be able to differentiate, and then we did a problem where it was analytic at 0. We did e to the x. We derived it. Then we derived cosine of x. And then we did a problem, I think we did cube root of x. And someone noticed right away, wait a minute. It's not analytic at 0. And it got really quiet. Is that the word? You know? And I said, exactly. It's not analytic at 0. So what should we, expand it by? And then someone said, 1. It's a good answer. And I had told them, every single time you ever did a Taylor series, you expanded it about 0 if you could. But if it's natural log, it's a root. No, none of the derivatives are defined as 0. Oh, so then you used 1, which turns out algebraically was the friendliest number that existed. And I said, we do the formulas generically. We always say x minus c, and that's correct. But c is always going to be 0 except when it's 1. You're never going to use any other number, so I don't know why we make it so abstract and ambiguous to say, well, I just did an entire course and we never used anything but 0. Or, right? In this case, we're not going to use anything but 0. So we don't need the general forms of things. We just need to know, is this good at 0? Now, let's see. Let's suppose we're looking at a specific value, okay? Very specifically, okay, so where this is analytic, okay, where this is analytic, and again, we're mostly interested in 0, is called, I'll put x values where P and Q are analytic. Common mistake is people will say x is analytic. No. The functions are analytic, not the variable. The x values where P and Q are analytic, and by the way, they both have to be analytic, are called ordinary points. Now, I don't like the term points. I'd rather ordinary values because they're not points. It's kind of loose right now. If it's not an ordinary point, let's suppose, for example, that there was an x here. okay, then this thing would no longer be analytic at 0. Let's say this is x minus 1 in front. Then it's not analytic at 1. It's not analytic at 1 would mean that 1 is a singular point. Okay? We are only working right now with ordinary points. Next day we're going to be talking about singular points. That's why I said next day's lecture is going to be a little bit trickier. Singular. Is that an odd use of the term, or is that a good use of the term? You've all had linear algebra. A singular matrix is a matrix
That equals its, no, it doesn't.
whose determinant is 0. Okay? So if you, there's a couple of different ways to find the inverse of a matrix. Okay, one of them, how many learned how to use an adjoint? That's, if it's 3 by 3, it's not bad. 4 by 4, don't do that, it's too long. But it's really nice, but what happens is you multiply your cofactor, the transpose of your cofactor matrix, you multiply by 1 over the determinant. But what if your determinant is 0? Then it technically means you're literally dividing by 0. The term singular in English means one of something, but in math and science, singular literally means you're trying to divide by 0. That's not a joke. That's what the term means. So I'll give you the simplest example because I do this in linear, right? A star dies. You know, kind of like the one in the Avengers. Remember the star where they made all this stuff, you know, and the gigantic dwarf, Peter Dinklage, remember? He's like 8-foot tall dwarf. I really don't really get that part. But the star dies. What happens with the star? Eventually it collapses upon itself. Now, the mass of the star does not change. But gravitational pull, as we know, is based on two things. The mass of the objects and the distance. Well, if the star is collapsing, then you can get much, much closer to the star, which means its gravitational pull is increasing. And as the star is collapsing and collapsing and collapsing, its density is growing without bound. As the star gets smaller and smaller and smaller, its density is going higher and higher and higher. And we say the star is literally collapsing to 1 point. Literally, which means its density is approaching infinity. And when that happens, in theory, that creates what we call a singularity in space, or a what?
Black hole.
Black hole. It's theoretical, because I'm pretty sure we don't have like a shuttle that takes us to the black hole. We can check it out and measure things. But the concept is the singularity is because we were essentially dividing by the mass as the mass was approaching 0. I'm sorry, the volume, not the mass. Sorry, it's mass divided by volume. Sorry, the volume is approaching 0. Now, does it ever reach 0? No, but that's the whole point. Is this creating this weird situation in space? We believe we know where some black holes are by the lack of anything else for really great distances. I mean, I guess that's one way. You know, so you're looking at an empty classroom. I don't know you can say there's a black hole in there because there's no people, but it's kind of the same idea. So why do we call it a singular point? Because it was 0 here, we divided and it created, oh, okay, it's not analytic. It's the same meaning of singular as we use in linear algebra. Okay, and I want you to know that because I don't want you to get confused. Every value I can consider is either an ordinary or a singular point. Now, what we're going to do is we're going to break down the singular points. There's 2 types of singular points we're going to look at next year. They're called regular and irregular. He's like, really? It's a bad number? We're going to break it into 2 categories? You know, less bad, more bad? Yeah, kind of. Okay, so that's new vocab, and we will extend that next day. So now I want to do, before I do the next problem, I'm going to show you an algebraic manipulation of factorials that I learned a million years ago. I'm not taking credit for this, but I don't remember where and who. But I've never seen it in any textbook, and every textbook where this comes up, particularly the binomial expansions that come right after Taylor series. It's my next lecture in Calc 2. Every textbook on planet Earth gets this completely wrong. And our textbook gets this completely wrong too. It does one example, and it's a bad answer. It's not that the math is incorrect, it's that literally the person writing the problem doesn't know there is a way of doing things. So I want you to consider the following. If you were in like Calc 2, you've seen this. I want to consider the following. Oops, not 8, sorry. That's not the next even number. I want to multiply the first n positive even numbers. So you were in Calc 2 with me, probably. So you've seen this. I don't expect you to remember this. But the manipulation is not very hard. Now, I would love a closed form of this. Not quite a factorial, is it?
No.
You see something there?
Yeah.
What is it?
It's factorial if you factor out a 2.
How many twos?
And
And 2.
Ooh, well, that's kind of convenient. You like that? That's not the one we're going to use, though. No, we're going to use the uglier one.
2.
This is the one that truly gives us issues. And nothing to factor out here. Boy, I'd love it if that was factorial-ish. Well, for that to be factorial, I would have to multiply it by 2 times 4 all the way up to 2n. Over 2 times 4 all the way up to 2n. What do you think? Would that work? So the product of 1, 3, 5 all the way up to 2n minus 1, that means the first n positive odd integers. Can you tell me exactly what this equals? What's the top? You just filled in the blanks, so what's the top? It's 1, 2, 3, 4, 5 all the way up to 2n? Product?
Maybe
Something factorial?
Oh.
How about 2n factorial on top? I did 1, 3, 5. Imagine it's the first 100. So 1, 3, 5 all the way up to 199. And then I just multiplied it by 2, 4, 6, 8 all the way up to 200. So I now have 1 to 200
Yes.
over,
that one.
2 and
and this is a closed form of the product of the odds. It's not the evens that are going to come up. It's actually the odds that come up. But we start with this. Now, this is an absolutely valid, simple, legitimate formula. What most of the textbooks do is they write their answer in this form, which I don't like. It's not a useful form. It's not that it's wrong, it's hard to interpret. Because, for example, the first one might have a 1, and then the next one has a 1 times 3, and the next one a 1, 3, 5. But they'll write it as all answers are in that form, yet not all those numbers are going to be used. You're only going to use one of them at a time. It is what it is. Okay. So the problem I want to do, that's fine, hold on a second. Okay, here's the problem we want to do. This does not simplify. You can't cancel the factorials because they're different. All right, so keeping that off to the side. The problem I want to do is x squared plus 1 okay. Is this analytic everywhere?
No.
yeah.
Oh, yeah,
Well,
Yeah, it is.
yeah, because it can only equal 0 at I and
You
negative
can't get a
I.
real value. of
So
0.
is it analytic everywhere?
Yes.
In the real number line.
Okay, it's analytic for all real numbers, but is it analytic everywhere? No, it's not analytic at plus or minus I, but that will present no issues at all. And by the way, that actually becomes very important next day.
No.
But the plus or minus I isn't a problem because that's, right, it's really, 0 is the only thing I was truly worried about. This is analytic for all real numbers. And for all practical purposes, that's okay. I would like to say it's analytic everywhere. It's not because there are 2 imaginary numbers that fail, but we're never going to worry about expanding about those. So for all practical purposes. But I like you both were correct. So we have to consider the effect a complex number can have. And in this case, it doesn't have an effect. Now, I'm not going to divide through. No, dividing through is to determine ordinary points. And we're going to leave it in this form. So we're going to start by, let's suppose y is the sum. Now, sometimes I'll use A, sometimes I'll use C. Don't worry about it. Sometimes you look and go, in the notes you'd use the C, and maybe, then just to mess you up, I'll use a B. Doesn't really matter. I'll use an A today. Okay, then dy dx is n a n x to the n minus 1. Technically, could I write a 0 there? Would it be wrong if I wrote a 0 there?
Yes.
You get an x to the negative 1 for your first term.
Well, but I'd also get a 0 as my first term,
Oh,
and the
okay.
first term of a series can't be 0. That's why we start at 1. Would it give me a wrong thing if I put a 0 there?
No.
No, but it also would make it harder when I'm trying to line things up. Remember, they have to start at the same place. And if I started at n equals 0, it will give the illusion that this is actually starting at 0. It isn't. It's actually starting at 1. So I do want to put the 1 there. Because I'm going to have to do a shift, perhaps. And if I started at 0, that shift is going to not work very well. Just want to make sure we got that part. Next day, we're going to be looking at things that we're going to add a constant to this exponent. That constant very well may be a fraction, in which case I will start at 0 because my first term won't be 0 anymore, necessarily. For example, if I put n plus r there, then I'm going to have an n plus r, which won't be 0 when n equals 0. So next day, everything's going to be a bit different. I said it's going to be a little more complicated. It's okay, we have time. Okay, so we've got this set up. Now we want to substitute those into here, then gather the coefficients. Okay, it's not a fast process, but just don't be in too big of a hurry. So I've got x squared plus 1 and then x n here. And then the last one is just now if I could combine all these I would. I can't yet. But you know, a lot of these are going to combine really well, aren't they? Because in the first one I have an x squared times an x to the n minus 2, and the next one I have an x times x to the n minus 1. Those are going to be great. That's going to be the problem child, that guy right there. We'll deal with it. So, let's multiply this in as two separate series, okay? So this will be, I'm going to multiply the x squared in first. I think I did that correctly. And then the next one, multiply it in. And then the last one. Now, the first, third, and fourth all have an x to the n, but they start at different places. The very first term here is going to be an x squared, isn't it?
Yes.
The very first term here is going to be a constant. The very first term here is going to be x to the first, and the very first term here is going to be a constant also. So my power series have to start as what is the first term? Think of like least common. One was a squared, one was an x, one was a constant, one was an x, you know.
Probably use start as an x squared.
Gotta start with the x squared, because I can't make the x squared be an x or a constant.
Right.
But I can make these be x squareds. I can run off the first two terms here. Does everybody follow? That's what determines it. The lowest degree term here is x squared. I can't get a constant or an x out of this one. So that's what all of them will be bound by. Okay? So let's make all of them start at x squared, and hopefully the n, you know, this is n equal to, probably all of them will look like that at some point. So let's do the shift on this guy first. So we do the shift, what will it be?
It's gonna be
Because then that'll be x to the n. So I replaced n minus 2 with n, so n plus 2, n plus 1, oops, not enough room there, sorry. A, n plus 2. Okay, everybody cool with that? Okay, stare at that. What's my first term going to be? 2 times 1 times a2. 2 times 1 times a2. That's how you always check it. Don't assume you did it right. Always check it, because the check is real easy. The problem is I might go in the wrong direction. Okay, so I've got this, I've got this, I've got this, I've got this. Okay? So all of them have points, they'll have an x to the n now, but they all start at different places. So I got the x to the n part covered. I don't have to change any more terms. This stuff is going to stay the same, same. Now I just have to make sure they all start at the same place. And we said we need each of them to have x squared as their first term.
Right.
So I don't have to do anything to the first one. What am I going to do here?
Yes, I get the constants out.
There's two terms. Hopefully you all see that. So what's the first two terms?
2 times 1
So
times
2a2
3 to 6
so 6a3x,
plus the
and then it's same, everything's exactly the same, but now where am I starting?
x2.
At 2. So we got the exponents to match, and then we're going to get the starting point. Getting the starting points to match is the easiest part. And that means just run off terms. What are you going to do here?
You plug in the first.
One term?
Yeah.
So what will that be? 1 times a1,
X.
x to the first, and now I'm going to add it to n equal 2 to infinity n a n x to the n. I probably should be using different colors. And now this guy. First two terms again? So what's the first one?
1.
So it's a0 and then a1x. Okay, stop me if you are in any way not certain of what we just did. So, we just substituted that. We didn't do anything yet. We haven't done nothing. Now I just distributed this. Okay, we still haven't done anything. I am now making sure all of them are x squared by doing a shift, or excuse me, x to the n. All of them, except this one, were already x to the n, so we started it, now it's x to the n. Now the problem is I have 3 different starting points. So now I made all of them start at n equal 2, so the first term of the power series would be an x squared. And then I have these other terms in front. Remember, we're setting the whole thing equal to 0 at some point, so we need to gather terms. So now, what are the constant terms? I'm going to bring it over here. What are the constant terms?
2a2.
And let's
A0.
do this one. Do we have any more?
A0. That's it.
Okay, so put those together. Do I have any linear terms? Yeah, I think we have 3. Do we have a1x twice?
Yeah, and it'll cancel out.
Oh, because that's a... Oh,
Yeah.
actually, you know what? That matters. Why?
Oh, that's minus.
That should be a minus. Ooh, I'm glad we caught that. That would have... If I didn't catch that, we'd basically be doing this problem with a plus sign. That'd be a completely different problem, and that
That's
don't work.
15 points.
Okay, so the A1X's are going to cancel. Do we agree?
Yes.
Mhm.
So what am I left with? Just
6, 6, A, 3, X.
Is there anything else that we have that's remaining? I don't think so.
Nay.
All right, now let's put everything together. So we're going to add up the coefficients, factor out the x to the n completely. So what does that leave us with? It's an n plus 2, n plus 1, a, n plus 2. I'm going to go ahead and erase this because we've already used it. I hate erasing, but I don't want to go to the other side of the board yet.
Could we factor out an, or can you not factor that out?
Yeah, we can. Let's put everything together first, though, because I think we might lose our... Yes, we can, but I'm afraid if I try to do too many things, we're going to mess up.
Factoring out x to the n.
So I just took out, yeah, x to the n we're factoring out. So I'm adding up that coefficient. Oh,
Up there in the blue.
we almost forgot,
That.
sorry, we have this coefficient too, don't we?
Yes.
Okay, I'll put it here. It doesn't matter what order I write them in. So we've got those two, right? And we have NaN, and then a minus AN. You're saying, can we factor out the AN? Yeah, but we also have another one over here, so we might want to put those together before we factor them out. Okay, everyone stare at this, tell me if this is correct. I don't want any boo-boos.
Where
Did
did that
we write it?
second AN come from?
So N times N minus one AN, that was the very first time I just wrote it, second. And then we have N plus two, N plus one, AN plus two. Then we have NaN, and then we have minus AN. I believe this is correct. Everybody okay with that? So here's what I want to do now. Let's put all that together. Okay, so what have I got? Well, I've got n squared minus n plus n minus 1. Is that correct? That's kind of not too bad. Would you agree?
Right.
That's n squared minus 1.
Right.
So could I write that as n plus 1 n minus 1 an?
Yes.
Ooh. This is looking less terrible. Now, what must be true? All of this has to equal
0.
0, because the power series can only equal 0 if each coefficient is 0. And don't confuse that with all of my ANs in this. A0, A1, A2, they're all 0. No, that combination is 0. The A's themselves don't have to be 0. They could be, but they don't have to be 0 to make the sum equal 0.
Sorry, can you repeat what you said?
Yeah, because this is true, that means this is 0, this coefficient is 0, and this coefficient has to be 0.
Okay.
But it doesn't mean that A0, A1, A2, A3, and so on. It doesn't mean that those are all 0. In theory, they could be, but if that's the only way I'm going to solve this is to make, then basically I'm saying my solution is y equals 0. Well, yeah, y equals 0 will work, but I think there are non-trivial solutions, and that's kind of what we're interested in. So when I put these together, this plus this equals 0. So can I just say, I'm going to throw it on the other side and then divide through. So I'd have n plus 1, n minus 1 over n plus 2, n plus 1, all times an. Yeah. This is all equal to 0, so I'm throwing this on the other side of the equals and then dividing through. Oh, and just so happened I can do that.
Oh.
Okay, you with me so far? So what do we got? We have a recursion. I think I need to... Okay, God, I hope we didn't make a mistake, because I'm going to erase this. I need the space. If we made a mistake and you're holding on to it, I'm going to beat you mercilessly later on.
Oh, you
Okay.
mean like the stock market?
What's that?
You mean like the stock market?
Okay, so what have we got? We've got a n plus 2 equals the negative of n minus 1 over n plus 2,
We made the whole story too.
a 0. Now, I'm sorry, not a 0,
That's what we
a n. If we were given an initial condition, and I will probably go back at some point and say, okay, now let's do the same problem with these initial conditions. Initial conditions are the easiest part. We don't want to get caught up on that. Right now, our answer is just going to have a0 times something in all likelihood. So now I want to start doing this, but you notice they skip by 2, so all the evens will go together like before, and all the odds will go together. Okay, everybody with me on that? So let's start off with, let's do the evens first, since it's right there in front of us. So what is a2? That means n is 0.
One half AN.
1/2 a
A0.
a0. So then what's a4? That means n is 2.
3, that's 6. Ah, it's 3 over 6.
If n is 2, no, n is 2, so it'd be negative 1 over 4.
Oh, right.
a 2, but that's negative a fourth times a half a 0.
Right.
So far, so good? Okay. A 6, that means n is now 4.
Yes.
N is now 4, so that's a minus. I think some of you are looking at it as a plus.
No, it's a minus.
It is a minus, isn't
It's a
it?
minus.
I did write it down correctly. Okay.
it's
So
one-
that's 3 over 6?
3 over 6, yeah.
So that's negative 3 over 6 a4, which would be
One.
negative, how about negative, or is it gonna be positive now? Sorry. Oh, it's not gonna, sorry,
Yeah,
it's gonna be positive 3 times 1 times 1 over 6 times 4 times 2. I'm not simplifying for a reason. We all want to simplify as we go, and that's always correct. And it completely eliminates any possible patterns. Remember we did this last day? We simplified it, and then I said, if we unsimplify, all of a sudden we saw exponential and factorial patterns. You know, there's no pattern yet. We do one more. So now n is 6, and so what do we got? Negative 5/8 a 6. Well, that's crazy. So that's now negative 5 times 3 times 1 times 1 over 8 times 6 times 4 times 2. Are you starting to see the emergence of something now?
No.
Odds.
Yes, the odd
I
factor.
was gonna say.
Evens.
Those are the two things that we worked out.
Do you see odds and evens both emerging right now? That's I'm hoping everybody sees that now. Okay? But if I had simplified as I went, I would see neither one. Therefore, I'd be writing my answer in ugly form.
Right.
Now, this is, think of this as 2n, if you will. So right now, n would be 4. But that's not 2n minus 1, that's 2n minus 3.
Blue. That count? Okay,
What if I stop at 2n minus 3? Then essentially I'm replacing n with n minus 1. Then this would be 2n minus 2 factorial. This would be n minus 1 factorial, and this would be 2 to the n minus 1. Still works. I'm just stopping one term sooner. Everybody understands that. So that's going to make that ugly. But I absolutely guarantee you we will be able to write a closed form final answer, because we can actually say, okay, then A2n is. I think we can actually say that right now. What is A2n? This, by the way, the author does this example, but doesn't go this far. And then his answer's got dot, dot, dots in the numerator. And I hate that answer, because you can pick it apart endlessly and say, this is just not going to work. Okay, so what's A2n? Well, my bottom is what? Oh, I think I erased that one.
2 times n factor. 2 to the.
This is the product of the first 2n positive integers, which was what? 2 to the n factorial. Positive, negative, positive, negative.
Negative 1 to the end to that.
Is it negative 1 to the n?
Ooh.
Which ones are positive and which ones are negative?
This,
I think it shifted by
so it's
1.
N minus 1.
By the way, what if we wrote n plus 1? Would that change anything?
No.
No, it'd still be the same thing. It's just, oh, okay. The evens are the negative. N was 4 and I got the negative. N was 3, I got the positive. So I need that to be shifted by 1. So what is that guy going to be? I told you what to do if it's the first n minus 1. So what if we stopped at 2n minus 3? Then it's not the first n, it's the first n minus 1 odds. Think of it this way. If I said go 1, 3, all the way up to 197, that's not the first 100 odds, that's the first 99 odds. But when I went from 2, 4, 6, 8 up to 200, that was the first 100 evens. So on the bottom, what do you notice? These are the first
4 even.
2, 4, 6, 8, 1, 3, 5. It doesn't go to 7. So it's not the first 4 odds, it's the first 3 odds. First 4 evens, but first 3 odds. First n evens, first n minus 1 odds. Does everybody see that?
Reasonable.
So there was that like other.
Yeah, that extra 1, it started 1 term later, think of it that way. But we could not have known that until we really got to here. You would not have seen it. Now you know, okay, so the next n would have been an 8. I would have a 7. Oh, right? And then the next one a 9. So you're going to see the pattern of odds continue. So what does that make my numerator? That thing there, but instead, what's it going to be? 2n minus 2 factorial over 2 to the n minus 1. By the way, we'll be able to clean this up nicely. And then the last one would be n minus 1 factorial. We will clean that up into one quotient. Things aren't going to cancel, things are going to combine. And it's going to be ugly. But that's okay, we can live with ugly.
Sorry.
Okay.
Well, actually,
This is the first n odds.
yeah, I guess it makes sense.
Well, think of it this way. Wouldn't I multiply this by 2, 4, 6 up to 198? So that's not 200 factorial, it's now 198 factorial. So in other words, it's not 2n factorial, it's 2n minus 2 factorial. Remember before I said, imagine you're going up to 200. So our n was the first 100 evens and first 100 odds?
I see it's not 199, that'd be n minus 1. 197 would be n minus 2.
No.
Like, for the odd, 199
Okay.
would be n minus
199 would be the 100th odd because
that'd be
200 is the 100th even.
Oh.
Remember, you're starting one less here. So this is the first 99 evens.
99 is okay, n minus 1.
So I'm multiplying this top and bottom by n minus 1 factorial. Or I'm sorry, 2n minus 2 factorial. What n? Before I said, just imagine we're doing the first 100 odds and the first 100 evens. That went up to 200 and 199, respectively. But now we're only going up, we're going one less odd, so it's one less even. So it's not 2n quantity factorial, it's 2n minus 2 quantity factorial. You're still not saying it.
So, yeah.
I'm stopping one odd sooner, which 2 digits sooner. So whatever factorial we had before has got to be 2 less, because I'm stopping 2 digits sooner. That's why I'm using the example of going up to, 2, 4, 6, 8 up to 200, 1, 3, 5, 7 up to 199. In each case, it's 100 evens, 100 odds.
And the bottom side is still n minus 1.
So now we're going one less, because if I'm multiplying top and bottom by this, okay, I'm multiplying top and bottom by this, which was what? 2 to the 99th and n minus 1 factorial. Or 99 factorial. 2 times 1, 2 times 2, 2 times 3, all the way up to 2 times 99. Okay, so can this be simplified? Yeah, these guys are just going downstairs, so now what have I got? I got negative 1 to the n minus 1, 2n minus 2 factorial, over 2 to the n, 2 to the n minus 1. We'll figure out what we want to do with that in a moment. N factorial, n minus 1 factorial. So this is the coefficient of a 2n then. Can anything be combined here?
Yes.
Well, yeah, I could do something with that. It's kind of ugly, but I can do something with that. What does this become?
2 to the 2n minus 1.
Yeah. If you wanted to really make this pretty, could you multiply top and bottom by 2 and just make that 2 to the 2n?
Yes.
Yeah. Would it really be better? Could I multiply top and bottom by n to make that n factorial? So now it's an n factorial squared? Yeah, but now I have an extra n on top that doesn't combine with this. So I'd be inclined to just leave this alone. Remember, if you were programming this into a computer, you now have a closed form. You don't have a dot, dot, dot. You have a closed form on your summation for your evens. So let's call the evens, how about y1? So what's y1 of x going to equal? Well, it's going to equal a0 plus a2x squared plus a4x to the fourth, dot, 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 forever and ever and ever. But we now know, what this is. Now, where does this start, by the way? Don't all of these start with x squared?
So that's a 2.
So when I set this up, I'm going to have a0 plus the summation. Because the summation, we just said, it starts with x squared. It doesn't start with the constant term. So that would be the first term. So now we'll figure out where to start it, but I'm going to put that down now. That big, I'm just going to write it like this. Okay. That a2n. X to the 2n, because only the even exponents. And where are we starting?
0.
Maybe 1.
Oh, 1.
1, because,
I already have 0.
by the way, that an is that.
Yikes.
That's the evens. Now, does anybody have the book with them?
I have it on my phone.
In the textbook, the author writes the answer as the sum of -1 to the n minus 1 of 1, 3, 5, dot, dot, 2n minus 3 over 2 to the n factorial x to the 2n. I hate this answer. You know why I hate this answer?
I could have done the close.
Because it's wrong when n is 1. It's wrong when n is 2. If n was 2, that means you finish out at 1. You don't have a 3 or a 5. Do you guys see a problem with that?
Yeah.
This isn't true until you're like, way down the line. Oh, now I got all those in-between odds. You're not starting with any of the in-between odds. When n is 1, that means you have your first one is a -1. Times 1 times 3 times 5 dot, dot, dot. You guys see a problem with that? Hopefully you see a problem with that. That's absolutely incorrect. If you're going to do this, then you need to start it way down the line to where these are actually included in your very first one to calculate. That's why I don't like it when textbooks do this. And by the way, how many of them do this? Everyone that exists that does series does this. This is a bad answer. This is a terrible answer. It's not correct. Sometimes you have no choice, but when I say the dot, 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 I mean more like I have this. I'm writing out the terms and I put dot, dot, dot. Because I can't write this as a closed form. That's what the dot, dot, dot is. I wrote out the first several terms. I never saw a pattern. I write dot, dot, dot. We discovered a pattern, and it's not that. It's that, exactly. Now here's the beauty. We're starting at 1. When n is 1, we're going to get the right term. When n is 2, we're going to get the right term. When n is 3, we're going to get the right term. How do I know? Because that's where all these guys are going to come from. Yeah,
Where
John.
did that x2n come from?
Oh, because we said we're only doing the even terms. We're not going to get any.
Isn't that what we just wrote on the right?
Those are the coefficients for the even terms.
Oh, okay.
But when I'm writing it out, we found a0, a2 is the coefficient of x squared, a4 is the coefficient of x to the fourth,
Oh,
and
okay.
so on. So if I wrote x to the n here, then I'd be having an x and x cubed and x fifth.
Okay.
It wouldn't match, would it?
Okay.
Now, if I wanted the odd coefficients, then I'd probably do 2n plus 1 or 2n minus 1. Now, we're going to do the odds in a moment. But we now know that is the evens for that guy. Now, real quick check, just to make sure, because could we have messed up in the simplification?
Me.
Might we mess up? Well, not you, but the person immediately to your right. Absolutely guaranteed. All right, n equals 1. Put a number in there. What do we get when n is 1?
Let's see. We get 0.
1, 0 factorial, okay. 2 to the first, 2 to the 0. That's 2.
Yeah.
1, 1.
Zero.
So after all that, we just get what? A half.
Good.
Oh, by the way, I'm sorry, I left it out. Times a0.
Yes.
Sorry, I left that part out. Aren't all of these?
Times a0.
Yeah, sorry, I got kind of sloppy. They're all times a0. Okay, what was our first term?
A zero.
Wasn't it 1/2 a zero?
Yes.
Okay, let's do another one. I don't think we have to do too many. N is 2. Negative 1,
4 and negative.
so negative of 2 factorial, N is 2. So I have 2 squared times 2, N is 2. So I have 2 factorial, 1 factorial. That would be,
Negative.
did I lose anything?
Yeah, it'd be,
Negative 1 over 8. That's good.
So what is that? That gives us 1
A0.
over negative 1/8 a0. Is that what we're supposed to get?
Yes.
Oh. How many more do you think we need to do?
One
No.
more.
We're probably good. Yeah, if it wasn't gonna work, it wouldn't have worked at all. Are you happy with that it works?
Yes.
If you're not doing what I just did, you're saying, I hope I did it right. No, you can be absolutely certain you did it right. We now have a closed form, not this. We have a closed form for the evens, but we haven't figured out the odds yet. So there is one little problem that we have not really been paying much attention to. Doesn't this have to equal 0? Well, how can that equal 0? Well, that means that A2 would have to be exactly what? 1/2 of A0.
No.
Isn't that what it is?
Mhm.
So do we have any problem with that? None whatsoever. But tell me about A3.
Oh, it has to equal 0.
A3 is 0.
Oh. This is going to be interesting.
Oh.
I think you're gonna like the odds better than the evens, just saying. All right, I'm gonna erase some of this stuff now. By the way, our recursion is true. When we set up this recursion didn't say n was odd or even, this just said this is the recursion.
Right.
So now let's look for odds. So let's start with n equal 1. So sorry, I'm starting with n equal 1. So A3 is then, n is 1. So what's A3?
Equals negative.
It's 0 times A1, correct?
Right.
Oh, and then what's A5? Well, let's say we're replacing n with a 3, so that's negative 2/5 A3, but wait a minute, A3 was 0.
So if it's always recursive,
How are you
then
getting
it
these
has to
odds?
be 0.
What are you looking at?
We're still using,
Oh, that one.
You
still using
started
that
at
one. A3, 5, 7, 9, 11. It skips 13, but then it comes back at, no, all the rest of the odds are 0.
Oh.
Are all the odds 0? No. A1 isn't 0.
That's true.
A1 is not 0.
We haven't checked out A1.
But A1 doesn't show up in the calculation. It can't. You can never assume if it doesn't show up. No, it's actually just the opposite. If it doesn't show up, what does that mean?
It could be.
It could be any real number. Yeah, this is even in linear algebra, right? If you have a column of zeros, we call that a free variable. It isn't 0. No, it's any real number. A1 can be any real number, and I would only know A1's exact value if I gave you an initial condition. A1 is not 0. But if that's the even part, so that was the evens. So let's call the odds. How about y2 of x? Well, then shouldn't that be a1x plus a3x cubed? Let me erase this here. Plus a5x to the 5th and so on.
Yes.
What did we just say about everything bigger than a3?
It's 0.
Oh, so what's my second solution?
A1x.
A1x. So the answer to this question is this plus this. Now, I wrote it somewhere.
What are you saying?
I had my summation somewhere. Let me rewrite my summation because I think I lost it. So right now I have A0 times the sum. Oh, and it was sorry, let me back up a little bit. I've erased too much stuff. I'm having a hard time finding my place here.
I mean, is this normal that like the y1s are evens and the y2s are odds, and then those would be two like y answers? Is that, like sine and cosine?
It is often the case, not always. You only have really two possibilities. My recursion is either going to be consecutive or every other. So it might have an plus 1 in terms of an. In this case, I had an plus 2. When it differs by 2, then all the evens go together, the odds go together. When they differ by 1, you don't, yeah, it's just one continuous thing. So right now, my evens, we just said, were that big ugly thing, which I'll just call A2n. Okay? And I'm starting at 1.
Plus A0.
The whole thing is times A0. So it would be A0 plus A0 times this. Why? Because every term was times A0. So if you want, a clean way of writing this would be that's fine also. Because once I know the value of A0, I would just put it in there. Plus A1x. That was my odd solutions. With initial conditions, I'd know the value of A0 and A1. The evens we had to work for. We had to work to get the evens. We didn't have to do too much work to get the odds. This will happen occasionally that you get lucky like this. Okay? This one was kind of gnarly, but the fact that we could write our answer in a closed form is very, very powerful, because now you can put that on a computer. Now, the question that came up last day, when we can get a power series, are we supposed to recognize what function it came from? Rarely. This is the power series. We have a closed form, but that doesn't look like any function I've ever seen. So I can't say, oh, and that's a sine or a cosine or an e to the x or an inverse tan or... No, it isn't any of those, but it is a closed form answer, which means it would be very easy now to write a computer algorithm to do the calculations for me, because I only have to enter the nth term. Does that make sense? That's why we prefer an answer of this form to an answer of this form. You don't have the choice. This problem, there was a pattern, we recognized the pattern, we took advantage of it. If I hadn't shown you the pattern with the odds and evens, would we have been able to write a closed form answer? The answer is no, absolutely not. You would have written it like the author did, the ugly version, which I'm not a big fan of because it actually has some inconsistencies to it. Okay? Kind of crazy stuff? Cool stuff?
Is that x to the fifth? Talking about odds?
Yeah, that would be a third, and then that'd be a fifth. Yeah, ugly writing. But what we just saw, though, was that all the odd coefficients were all 0, right? Starting with x3. How do you know starting with x3 they're 0? Well, for one thing, this term has to be 0, and there's only one value there. This term had to be 0, but there were 2 values. x0 and x2, neither are 0. It's just that x2 is 1/2 of x0. That's why this worked. But that x3 is sitting all by itself. It has to be 0. But now when I go back to the recursion, oh, when n is 1, a3 is 0 over 2 times a1. So that it's like I can see it in 2 different ways. By the way, what I'm showing you there, where we saw the relationship between a0 and a2, we got the same relationship there. It has to be the case. You can't possibly get different relationships. That means I royally messed it up. Where does this come from? From running the first couple terms off my series that produced that recursion. So it has to match. The A3 being 0 there, A3 being 0 there, it has to match. No other way around it. What if? What if there were 2 terms here? Then I'm probably going to get something similar. I'm going to get a nice little recursion, closed form, maybe not, maybe ugly. But this one ended up being nice. Yeah.
Where did that A2 come from? Because wasn't it before it was A0 plus A0 times summation?
Yeah, I think it's supposed to be a.
Oh, I'm sorry. I said A0, didn't I? Thank you. Yeah, I said A0, but I wrote A. Yeah, that's an A0 because it's the same A0. It's my first term is constant. Then the next term was an x squared. But remember, every term now is in terms of something times A0. Once I find the value, now whether I write A0 plus A0 times, it doesn't matter, because if I found the value of A0, I'd probably just go to distribute it and write it that way. In fact, if I found, let's just say A0 was 5. Well, then can I write 5 plus and just put the 5 right here? Or it doesn't matter. It's like, what's the prettiest form, I guess.
And then if there were another condition outside of that summation on the left board where it was like right after the 6a3x, it was like 8a4,
Oh, if there was another, yeah, I'd have to
where there's a
consider that
break-
one.
Where there's a break in the middle of that summation. where we just
I would have to
that.
consider all of those. And by the way, that's, running off a few terms and then having them in front always feels a little uncomfortable, but it actually sometimes makes it easier to solve because I got that standalone A3 being 0. I made everything nice. Can you do it in such a way that, let's suppose we did this and it turned out that everything was 0. Well, no, everything can't be 0. Y equals 0 can't be the only solution. Why? It's a second order. There has to be two linearly independent functions. But can one of the functions be a constant?
Yeah.
Yes, that is possible. It's kind of boring. One of my functions can be. Well, in this case, we got one function that was an infinite sum and the other function was just y equal x. And that's pretty low level. Let's just say hypothetically that this flipped and that the recursion occurred on the odds, not the evens, and the evens were all zeros. Then we would have had A0 in front and then no even terms ever again. And then we'd have a summation with the odds. So there'd be a perfect example. One of your functions would have been a summation, the other one would have been A0. That was literally your answer to the question, that constant. Not very exciting, but that is a possible answer. Okay, so it can happen, yeah.
Right, on the left we first start at n equals 2, so why not at the final answer of the n equals
Well, okay, because right now, we started at n equal 2, but these are also counting by 1. So it's x squared, x cubed, x fourth, x fifth, x sixth. But then we determined we're going to break it up odd and even.
Oh, right.
So now because I'm calling it 2n, n equal 1 means my first term is still x squared. So don't confuse it with the starting point. Go back and say, what's my first term? My first term is x squared. My first term is still x squared. So we didn't change that. But because I'm only looking at the evens now, I'm not going to start at 2 because my exponent already has the 2 in it.
So the sum inside is between the odds and the even, and you just...
Yeah, this answer is for all of the even coefficients, and this answer is for the only odd coefficient that survived, if you will. Okay.
Can you just go over one more time how you noticed the pattern in the numerator for the even side, where we had 5, 3, 1, 1?
Oh. Well, you're not seeing anything yet.
Yeah.
Okay, it's pretty obvious now because n's are evens, right? 2, 4, 6, 8, 10. So I'm going to see 1, 3, 5, 7, 9, and so on. But I had to do a few terms. But what I didn't do, I didn't simplify. I purposely did not simplify any of my fractions. Because then the denominator, I clearly see an even pattern.
Mm-hmm.
Again, 2, 4, 6, 8. But not until I got this 5, I think we agreed that we didn't really see the odds emerging. So if my bottom is a 2n, my top has got to be 2n minus 3, not 2n minus 1. So when I set up the little pattern at the beginning, I did it for 2n and 2n minus 1. So we had to back up one whole term, because that doesn't have a 7 here. And that's why we had to replace n with n minus 1 in the formulas. That's why, for the odd part. The even part, no, that came from there. That came from here. Now, what if that had been a 7? Well, then that would have been 2n factorial. 2 to the n, that would have been n factorial, just like the formula we derived earlier. But the beauty of this is that regardless of how ugly this is, I have a summation of one thing. And then we checked it, and it does produce the right coefficients. So now I would program this on a computer and have the computer now generate an infinite sum without me doing any more work. Now, my hands are clean. That's really the ultimate goal, is if I can write a closed form answer. This is a closed form. There's no dots in here. Then I can do any type of programming I want to do if that was my ultimate goal.
So if the pattern were like 5, 3, 1, 1, 1, where it starts 2 terms late, it would be 2n minus 3, and then it would be divided by 2n minus 2, n minus 2 factorial.
If you said, I clearly see an odd pattern, but it doesn't have as many terms as I need, then how many? So instead of instead of the first n odds, which end at 2n minus 1, oh, I have the first n minus 1 odds, so it ends at 2n minus 3. What if it was the first n minus 2 odds? Then it ends at, well, then I'd adjust appropriately, but I'd also probably have to start my sum a little later, because I run the risk, because I can't afford to have a negative exponent up there, all
Okay.
things being considered. This is an exceptional problem. This problem, there was no part of it that was hard. If we see a pattern, it allowed us to finish the answer. But it was, what I want you guys to see was the recursion, because these differ by 2, it's an automatic that odds and evens are separated. Because you're counting by 2s. You can't go from odd to even if you count by 2s. Could we have a recursion that counted by 3s? We could, but that one would be extremely difficult to find any kind of a formal pattern. So that's, you're probably writing a plus dot 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 answer, meaning we're writing an answer where I just give you the first several coefficients and then that's it. And unfortunately, most of the problems are probably that. So in real life, you'd find as many as you had time to find. And then just sort of leave that. Okay, let's go ahead and stop because I want to leave time for the review.